So thanks for the invitation to be here and to tell you a little bit about some of the innovations, ideas that might be coming down the pipes or are coming down the pipes in the development of new antibiotics. But before I start, I think one of the things, there's enough folks of my generation, you remember the Hair Club for Men, right? I'm not only the president, but I am actually a customer. Well, I'm not only a researcher in AMR, I've actually also been the victim of it. About 5 years ago, I ended up with a salmonella bacteremia that was food associated, so I'm a big fan of One Health idea. And that turned out to be ciprofloxacin resistant, which of course was what I was put on as the first run antibiotic. Luckily, IV ceftriaxone about 3 days later actually made life a lot easier for me. But I can tell you from personal experience, as a guy who's been working in this area for a long time, it's a very serious problem. And if you don't know the miracle of antibiotics, is you have to just wait for an hour after you've gotten your ceftriaxone, after you've been bacteremic for about 3 or 4 days, and then you will know just the wonder of antibiotics. It's really quite remarkable. So what we're trying to do is find new ones. All right. Oh, it's a big green one. So you've seen a version of this earlier in the first talk today, but it's a timeline. Where have we been and where are we going? You know, in the pre-antibiotic era, if you look at Statistics Canada data, 60% of us died of infection-related diseases, right? The world completely changes, as my experience shows you. In the 1940s, really, and 1930s with the sulfa drugs, but 40s when the so-called golden era of antibiotics, when the mycins, etc., were discovered, and then that was followed. We are now firmly in what I would call the resistance era, where we are not dominated by wonderful new discoveries. Instead, what we are seeing is the erosion of these discoveries over the last 6 or 7 decades. And our concern, of course, and why we're discussing this, is that we're at risk of entering into a post-antibiotic era. And you heard the dire statistics from the O'Neill report that no one really wants to visit that world. So why do we need new antibiotics? There's no such thing as a resistance-proof antibiotic. It does not exist, right? Resistance is ancient. We have shown that in permafrost, where we could find DNA associated with extinct mammals like mammoths that's 30,000 years old, the entire vancomycin resistance cluster that is now circulating in VRE was existent at the same time as mammoths back then. So this is an old problem. It's part of the ecology of microorganisms. Microorganisms not only transfer their genes from mother to daughter cells, they exchange DNA rapidly. And as Ed Top accurately pointed out, the resistance is incredibly broad in the environment, incredibly diverse. And every once in a while, capture of one of these elements into a pathogenic organism creates this problem with a selection pressure. At the end of the day, we cannot overcome evolution. So how did we find our antibiotics in the first place? So the first 2 antibiotics that we discovered were really penicillin and streptomycin. These ushered in this golden era of antibiotics. This is Selman Waxman, right here, who discovered streptomycin. Bit of controversy about that. If you're ever really interested in scientific controversies, you can look that up. He got the Nobel Prize by himself, perhaps not deservedly, for the discovery of streptomycin, which is the first drug to treat tuberculosis. Tuberculosis still kills millions of people a year in other parts of the world, but of course most of us have never even had to experience it. It turned out that these natural products that ushered in this golden era came from other microbes, and is likely the result of that ancient history of this competition between microorganisms. But by the 1960s, we kept finding the same old compounds over and over again. So the next 2 decades really were dominated by the ingenuity, the innovation of medicinal chemists to be able to take those scaffolds and make better drugs with them, improve their efficacies in humans, but also to overcome resistance. But that really spoiled us. We started using antibiotics for all sorts of ridiculous things. So you could make gum with it, or you could put it inside your deodorant. Or this is my favorite here. If you have a sore throat, you can get this stuff. These lozenges had bacitracin and colistin in them. They were sold over the counter. So you heard about the MCR1 problem. Colistin are literally, if you look up in your IV bag, it says colistin in it, things are going seriously south for you, right? It's a really toxic, old antibiotic, and yet we used it willy-nilly, not only in agriculture, as you've heard, but also for human activities like this. But of course, on a ton scale, the use of antibiotics in agriculture really has provided an opportunity for selection on a scale that microorganisms have never seen in their entire history. Right? So you have this tremendous evolutionary pressure going forward. So in the 1990s, we really thought that genomics was going to save our bacon. We can sequence microorganisms, we'll find all the great targets, we'll make new compounds, we'll use combinatorial chemistry and high-throughput screening. And as these really important reviews that came out in 2006 and 2015 from GSK and from AstraZeneca indicated, this approach yields no new drugs. There are no new drugs in the pipeline at all that have come from basically a quarter century of work using these technologies. So, now what? Well, I think it's really important to go back to the source where we actually got most of our drugs from in the first place. This is nature knocking us on the head and telling us where to find the next generation of antibiotics. I do not think we're going to ever be able to recreate the golden era of antibiotics, where every time you grew an organism, you could find a new tetracycline or a streptomycin or a neomycin or a vancomycin. Those days are over. These are broad-spectrum drugs, really non-toxic, all sorts of wonderful things with them. But I do think that there are chemical scaffolds that we can go back and find that now with 21st century technology, the ability to maybe use diagnostics to make sure we're treating the right bug with the right drug, right? That we are actually in a situation that the clinicians of the 1940s, when they didn't know what was causing the infection, could actually do it. So narrow spectrum antibiotics, for example. We also found out when we started sequencing the genomes of these microorganisms that live in the soil, that while we collect one or two compounds from them, they actually have the genetic programs to produce 30 or 40 different compounds, some of which, no doubt, are really important new drugs to be discovered. And so using now things like synthetic biology, we can actually start to pull these genetic programs out and use other platforms like yeast, like E. coli, like other organisms, and actually start to tame these wild gene clusters. The other option, of course, is that the antibiotics from the golden era are unbelievably good drugs, if only we didn't have resistance. So an important strategy going forward is to think about combinations. Can we combine antibiotics with inhibitors of resistance or with compounds that enhance the activity of antibiotics, say, inside the host? This idea is not a new idea. The combination of beta-lactam antibiotics with inhibitors of beta-lactamases, for example, is well proven, but you can actually still find new ones. So this is work from our lab. This is a fungus that we discovered while hiking one of my students discovered while hiking in Kedemkujik National Park in Nova Scotia. It turns out, you've heard the term NDM1. This turns out to be an outstanding inhibitor of NDM1. Actually works incredibly well in animals and is actually under preclinical development right now. But I'm sad to say that's happening not in Canada, where it was discovered, but in the United States, where the money is. So if we go back and look at this timeline, really our opportunity is not necessarily to enter into the post-antibiotic era, but perhaps an innovation era, where we can use new ideas to find new antibiotics, this idea of adjuvants, mixing molecules together, targets that are not necessarily essential on a petri dish, but inside the host. Combinations. Really, this needs to be driven together with diagnostics, as we just heard from Joanne's fantastic talk. and et cetera. And here we're going to hear from Bob about phage and vaccines and what have you. There's lots and lots of wonderful opportunities going forward if only we can just harness these ideas. So to do that, Bob Hancock and I have start to prime this pump. We wrote an op-ed this summer that was published in The Conversation and picked up by newspapers around Canada, including the National Post. And really what we said that we need to do is start a new network. We've talked about this, that is outside of anyone's special interest. Really all we're trying to do is bring together academics, the private sector, government, not-for-profits, all together with a goal of trying to solve this problem. So this is our website that is going to go live probably next week. Many of you have already signed up to be part of this. If you haven't and you're interested, then please let me know or send me an email, and I'll make sure that you continue to be part of the conversation. We need to solve this problem, but we need to solve it together. And I really do think that the time is right for Canada to be able to do their part in this global problem. Thank you.